Hello, everybody. Welcome back. Good afternoon. It's a pleasure to be here. I am where I always am, in my basement. We have our first homework assignment is due tonight. I hope you've had a chance to check it out. Submit it before midnight, and everything will be great. Let me know if you have questions. I'd be happy to try and help out by email or some other way. All right. Any brief questions about the homework?
Yeah, I have a question. So when you're, say, for number one, trying to write out the strings within a language based on the set notation, would all of these strings have that empty string in it?
Let me just look.
Like, I don't know if that was like a general rule for every language.
Yeah, right.
Empty strings
I'm trying to flip to the problem in my book. You talking about chapter 1?
Yeah.
Number
chapter
1?
one, exercise
Yeah.
1.
Okay. So.
Specifically part B, because it says like.
Yeah, part B should not include the empty string.
Okay.
Because B says any string like x, y, where x is a or aa, and y is aa or aaa. So this does not have the empty string in it because you can't make the empty string by combining, one of these with one of these, which is what that means. Everything in this set has to be either a or aa followed by a aa or aaa, and there's no way to get the empty string from that.
Okay, that makes sense. And
so
then
yeah, go ahead.
I was going to say, and then for like part D, when it says that you need something that's less than 20 and divisible by 3, the empty string wouldn't be divisible by 3 then too. So would that mean it wouldn't be in there as well? Or?
No, that one, I think the empty string is in there because it says a to the n, where n is less than 20 and n is divisible by 3. But so 0 does count as divisible by 3.
Oh, 0. Okay, so
yeah.
then n to the 0 would just be the empty string.
Yeah, right. Yep.
Okay.
Yeah.
Thank you.
Yeah, 0 is divisible by 3 because you can write 0 equals 3 times 0. So 0 is a multiple of 3. And so 0 is divisible by 3. Yeah, that's a bit of a technicality, but that's what it should be. Any other questions about those? Great. And whenever you see the little star, that also does include the empty string. So, all right, great. We were talking last time about a DFA based on strings of zeros and ones interpreted as numbers in binary. And I had made sort of a little chart at the end. I thought maybe we could just fill this in again real quick. On the left, you see ordinary decimal numbers. Decimal meaning base 10. Remember, that means that we count up. We have a separate digit written for every value 0 through 9. But when you get to 10, 10 does not have its own digit. You carry over to the next position. So binary is just like that, only the base is 2, which means we have digits for 0 and 1. But once we get to 2, we carry over, which means in binary you do a lot of carries. So we begin with 0 and 1, but then 2 in binary looks like 10. The next number up is 11. And then the next number up has to carry, and it carries all the way over, and we get 100. Next would be 101, then 110, then 111. And then next we carry over to the next digit. And so on. I hope that this makes some kind of sense. And there are people out there who are like serious binary experts. I am not. I have to think kind of hard about converting from one to the other. And we are not. I don't care if you're good at that or not. All right. Any basic questions about the binary number system? All right. Computers do everything at a very basic level. They do everything in terms of binary. More often for computer binary, we more often write things in what's called hexadecimal, or hex is written, that's a base 16. So in each digit you have a separate digit marker for 0 through 15. And they use A, B, C, D, E, and F for hex digits. That's why a lot of computer, like you might see like default Wi-Fi passcodes. They look something like 13A to 4BD05F or something. You may notice they only use the letters up through F. That's because hex is base 16, and after F you carry over to the next digit. Anyway, I don't know if you care about that. What I want to do is make a DFA which accepts a binary string which represents a number which is divisible by 3. So a DFA on the alphabet 0 and 1. Oops. 0 and 1, which accepts a binary number divisible by 3. All right. And what makes this tricky is, just like I said last time, I don't even know myself how to tell if a binary number is divisible by 3 or not. The only way that I really would be able to do that is by converting binary to decimal and then checking if the decimal number is divisible by 3. But a DFA, that is a complicated procedure, which I wouldn't want to create a DFA to do that. It turns out, though, that it's not so hard to make a DFA to do this kind of directly from the binary strings. And the first big idea that I would like to have about this is... this garbage over here. My first big idea is when you want to see if a number is divisible by 3, you know, some numbers are divisible by 3, some are not. So you could say there's like two kinds of numbers as far as divisible by 3 goes. They are divisible or they aren't. But you can be a little more specific in a way which is helpful for a problem like this. And I'm going to say when we divide by 3, there are really 3 categories of numbers that you get. There are 3 types. They are ones where I will say some x are divisible. All right? But there's 2 other categories. The ones which are not divisible, either they are not divisible and when you try to divide by 3, you get a remainder of 1. Or there are numbers which are not divisible, and when you divide by 3, you get a remainder of 2. This is something you probably talked about in your discrete math class. There's something called the division algorithm or the quotient and remainder theorem. It says when you divide any number, for instance, by 3, it can divide and you get a remainder which is either 0, 1, or 2. So some are divisible. I'm going to say some x have remainder 1. And some x have remainder 2, all right? And the fancy language that we use for this, which I think that you've seen before, is this. We can say x equals 0 mod 3. That means that it is divisible by 3. When you divide it by 3, you get no remainder. Or x equals 1 mod 3. That means when you divide by 3, you get one remainder equal to 1. Or x equal 2 mod 3. And these are all the options when it comes to dividing a number by 3. Right? These are all the possible, answers or results you could get when you try to divide a number by 3. It turns out we can make a DFA in 3 states based on these 3 categories of numbers. So this is the big hint. You know, this is a difficult DFA to just come up with out of nowhere, but I hope you will accept a friendly hint. These are going to be the 3 states which we're going to consider when it comes to analyzing numbers and their divisibility by 3. So I'm going to draw a diagram with 3 states, and I'm going to label them in this way. X equals 0 mod 3, x equal 1 mod 3, and x equal 2 mod 3. All right? And the idea is as you read the string, it's another very strange thing about this DFA is it's going to have to decide, for example, is this number divisible by 3 or not when you read this in binary? Well, 1011, if I look on my chart, is 11. So it is not divisible by 3. This is not divisible by 3, right? Because 1011 in binary is 11. One thing that concerns me even more than trying to figure this out is your DFA, it has to read the string from left to right, which is a little crazy, right? I mean, when we all know that when you read numbers, you kind of have to read them from right to left. Like reading a number from left to right, you don't even know what digit this is. When you start reading this number, you see 1. But you know, because I can already see the whole number, I know this is the 4th digit over, but the DFA will not be able to know that. So this is a very, very strange setup. We have to read the number kind of backwards, the DFA. By the way, anybody happen to know, just like historically speaking, why do numbers, when we write the numbers, we kind of write numbers backwards? Like the rightmost digit is sort of what we would ordinarily think of as the first digit, but we put it all the way on the right. Anyone know why is that? A little historical, linguistic. It's because
we read left to right.
Well, yeah, we read left to right, but our numbers grow from right to left. This is weird. Like an ordinary word that we read, if you make the word longer, it stretches out further to the right. But a number, when you make the number bigger, it will stretch out further to the left, which is kind of backwards. Wouldn't it make more sense if we wrote them the other way around? The answer is kind of it would make more sense if we wrote them the other way around. The reason that we write numbers the way we do is because they come from Arabic, which is a right to left language. So it made sense to the Arabic writers to do it that way. To us, it makes less sense, although we're so used to it that we don't think about it. But it's a little historical artifact of the Arabic influence on our notation for numbers. Okay. All right. Let's just see if we can sort of say some details about this. This is a DFA, right? Maybe we can decide for just to get started. What should be the accepting state in this DFA? Remember, I said we want to accept any string which is a number that's divisible by 3. So which one should be the accepting state?
The first one?
Yeah, the first one on the left. Surely you mean on the left when you say the first one. That's because you're used to writing things from left to right. Yeah, that should be the accepting state because this is a number which is divisible by 3. That means x is 0 mod 3. How about the starting state? This one you need to have a little bit of interpretation, but what if you sort of want to think about the empty string? Should we consider, if we consider the empty string as if it were a number, should that be considered to be divisible by 3, or is it 1 mod 3, or is it 2 mod 3? Any thoughts on that?
Would it be divisible by 3 because it's 0?
Yeah, right. I think it makes sense to interpret the empty string as the number 0, in which case it is divisible by 3. So the starting state should be here also. Oops, I turned blue somehow. The starting state should be here also. That's because the empty string, which is kind of where we begin with no letters, should be, it doesn't make sense to think of it any other way. It should be interpreted as the number 0, which is divisible by 3. Okay, really the question is now, so I would like to know, for example, over here, where is the outgoing arrow with a 1? Where does it go? Does it go across? Does it go back here? And also, where should the outgoing arrow with a 0 be? These are the questions we need to answer. Really what we need to think about is something like this. If x is a binary number, and we stick a 1 on the right side of it, on the right end, how does the value change? Because you have to imagine your DFA is going to read from left to right, and so each new letter that the DFA reads, either a 0 or a 1, sort of changes the value that it's going to interpret of this big number. If we stick a 1 on the right end, and then also, or if we stick a 0 on the right end, same question, all right? Maybe we could just think about this as an example. How about, what if I start with 1, 0, 1, which is the binary number, this is 9 in decimal. Actually, can I make it smaller? How about just 1, 1? That's the number 7, isn't it? No, that's 5. Is it? What? See, I told you I was bad at this.
1, 1
3.
is 3.
It's 3. All right, thank you.
And 1, 0, 1 is only 5.
Yeah, I was off by a digit. Okay, so I could have done that. That one wasn't too big. Anyway, what happens to this number if I were to add a 0 on the end of it? Or if I were to add a 1 on the end of it? Of course, it becomes 1, 1, 0. This number in decimal is, this is 6, right? And this is 7. That was one example. What if I did 101? This is the number 5. And if you add a 0 on the end of it, it becomes 1010. And if I add a 1 on the end of it, it becomes 1011. This is 10. This is 11. Can anybody see a pattern here? Can you say in general, what happens to the value of the number if I add a 0 on the end? That one is a little easier to think of. What happens to the value of a number if I add a 0 on the end?
Doubles.
It doubles. Yeah, that's it's certainly true in this example, right? Here it was a 3. I stuck a 0 on the end, I get a 6. Here it was a 5. I stick a 0 on the end, I get a 10. Can anybody say why that should be true? It is true. This sticking a 0 on the end has the effect of doubling the number. Anybody have a... perhaps?
It's base 2.
Yeah, this is because it's base 2 that we're using these numbers in. This is analogous to the fact that in decimal, base 10, if you stick a 0 on the end of a number, the effect is to multiply the whole number by 10, right? In binary, if you stick a 0 on the end of the number, the effect is to multiply the whole number by 2. It's because when we write the numbers, for instance, in decimal, each digit position refers to a power of 10. If you stick an extra 0 on the end, you are increasing the powers of all those 10s by 1, just to say you're multiplying by 10. Same idea in binary. So my conclusion is, if we stick a 0 on the end, it doubles the number. And if we stick a 1 on the end, can anybody say what it does in that case? If we stick a 1 on the end?
It doubles plus 1.
Yeah, if you stick a 1 on the end, that's just 1 more than if you had stuck a 0 on the end. So there's not a great way to say that, but it doubles, like she said, plus 1. All right? Excellent. So we are beginning to understand a little bit about how this thing, what happens when you're reading a number from left to right in binary. I don't generally suggest reading numbers in that way, but we can answer questions about which way should the arrows go. So I would like to know, from the starting state, which way should the outgoing arrow go with a 0 on it? So the way to answer that is, I have to ask myself, first of all, if x equals 0 mod 3, and I stick a 0 on the end, I get instead now 2x, right? It used to be x, but I stick a 0 on the end, so now the number becomes 2x. And I would like to know, is this number now still divisible by 3, or is its remainder now 1, or is its remainder now 2? What do you think? If I had a number, it was divisible by 3, and then I double it, is it still divisible by 3?
Wait, Professor, what's the word at the end of 0 on the...
On the end. I stick a 0 on the end. Yeah, I got a little excited there on the end.
It would still be divisible by 3.
It would still be divisible by 3. Yeah, this is how divisibility works. If it was divisible by 3 and then you double it, it's still going to be divisible by 3. I would say, oops, then 2x is still divisible by 3. All right? And so that means on our original diagram, if your number is divisible by 3 and you read a 0, it should still be divisible by 3. So on my original diagram, sorry, I keep going back up. I'm sure it's easier for you to just glance back and forth. It's like that, right? If it's divisible by 3 and you read a 0, the result is still divisible by 3, okay? And we're just going to try and do the same sort of reasoning for all the various other, things that you might do to this number, okay? So the other case would be if it's divisible by 3. Let me, I would just like to, instead of all of these words, I would like to write this a little more kind of mathematically, which will make it easier to repeat this reasoning in the other steps. can I say it this way? If x equals 0 mod 3, then we can say x equals 3 times k, right? And so what is 2x? 2x is 2 times 3 times k, which is 3 times 2k, which is, I'll say it this way, 2x is 0 mod 3, right? Just a little more algebraic way of writing the same thing again. This, I suppose this would constitute a proof that the 2x is still divisible by 3, because you can still factor 3 out of 2x, okay? All right, let's try the arrow with the 1. This way, I would say, can I just say, if x is 3k, that is, it is divisible by 3, then I need to consider 2x. What is 2x? No, sorry. Whoa. What happened? What happened? All right. I'm going to consider 2x plus 1. Remember, when you stick a 1 on the end of the number, it turns it into 2x plus 1. It doubles and then adds 1. What can you say about this number in terms of divisibility by 3? Well, this is 2 times 3k plus 1. And you can rearrange again. 3 times 2k plus 1. And I conclude that this is 1 more than a multiple of 3, right? That is to say, this equals 1 mod 3, because I wrote this thing as 3 times something plus 1. So this number here equals 1 mod 3. All right? And that means the other arrow on my DFA from the starting state should go across to the 1 mod 3 state, because if you do 2x plus 1, changes the value to 1 mod 3. So on my diagram, I get one of these, like that. All right. And we're going to do this, I guess, 2 more times. There's a total of 4 more arrows to draw in here. So let's see about from here. If we do the 0 arrow, where should it go? Should it go a loop here or back there or perhaps over to the right? Let's try it out. So from x equal 1 mod 3, right? So let's do the 0 arrow. When I say x equals 1 mod 3, that means x equals 3k plus 1, right? That's what it means to say x is 1 mod 3. It's 1 more than a multiple of 3. And for the 0 arrow, we need to decide what happens if I double it. Well, that would be 2 times 3k plus 1. What do you do with that? You got to distribute. We're not going to do a lot of this distributing or whatever in this class, but I hope you know how to distribute. You go 2 times 3k plus 2, which is 2k plus 2. So what do you say about this this arrow, the 0 arrow from the middle state? Should it stay where it is, go to the left, or go to the right? What do you think?
Should go to 2 mod 3.
Yeah, it should go to the right, because this thing, after doubling this, we end up with a multiple of 3 plus 2 extra. And so this thing is 2 mod 3. So this arrow with the 0 on it goes like so, right? Everybody hip to what's going on here? Any questions so far? We're going to just sort of do the same thing 3 more times, but it's not going to get any harder. All right, let's try from the middle state, the arrow with a 1 on it. This one, so this is the 1 arrow. When you do the 1, you turn the number into 2x plus 1, and we just have to work out, what is this value when I go mod 3? Well, it's 2 times 3k plus 1 plus 1. Rearrange this business here. I get 6k plus 2 plus 1. This is 6k plus 3. Right? What do you say? Is this Is it divisible by 3? I think this is divisible by 3, isn't it? I can factor 3 out of the whole thing. So this is 0 mod 3. All right, and that means the arrow with a 1 on it in the middle goes back to the left to the 0 mod 3 state. Like that. All right. I'm feeling good about this. All right, let's just add. We need 2 arrows from this guy, and that should do it, right? So from the x equals 2 mod 3. Okay, so for x equals 2 mod 3, this means x can be written like 3k plus 2, right? That's what it means. That x is 2 more than a multiple of 3. For the 0 arrow, I have to decide what 2x looks like. 2x would be 2 times 3k plus 2, which is 6k plus 4. What is this in terms of mod 3? Is it 0, 1, or 2? See a lot of people.
Can we just speak up?
Yes, please do.
Is it 1 mod 3?
It is 1. Yeah, that's right. Because of this 4, I mean, you could say the 6 definitely is a multiple of 3. So you could say this is 4 mod 3. But 4, of course, is the same as 1 mod 3, right? If you want to reason it in that way. Yeah. So that means this arrow, the 0 arrow from the rightmost state, goes back to the middle, the 1 mod 3 state. So scrolling up like so. All right. And then I have, no, that was the 0 arrow. Sorry, I wrote it wrong. 0, like that. All right, and one more arrow. From the rightmost state, what happens when we do a 1? Here I go, the 1 arrow, it's going to say 2x plus 1, which is 2, 3k plus 2 plus 1. Rearrange this, 6k plus 4 plus 1. This is 6k plus 5, which when we divide everything by 3, we end up with a leftover of 5 mod 3, but that's the same as a leftover of 2 mod 3. And so when I have the arrow with the 1 on it, it stays as a looped edge on the right side. And this, my friends, is the answer, right? This is a bit of a journey to get there, but this is the DFA, which can tell if a binary number is divisible by 3 or not. It really works. Let's see, can we do a quick example here? How about 9? 9 is divisible by 3. 9 is 1001. What do we get? You start here, right? And I go 1001. I'm back here, which is accepted, right? I hope my audio is in sync so you can see my dancing dot. 1001 is accepted. All right, versus something like 1011. That's 11. It should be rejected because 11 is not divisible by 3. And if I start here, I go 1011, and that's rejected. So it is doing the right thing. All right. Any questions about that? That's a big example. It took about 30 minutes to do that. I hope it was worth it. I kind of like this. Like I said, I wanted this to be an example of a DFA which can do something which seems like a useful computation, even though it's a computation that, like, I personally wouldn't be able to do in my head. I mean, I might if I really had to, but it's not an easy thing to do. But as far as DFAs go, this is a very simple one. Only 3 states. All right. Any questions about that? Anything to discuss? Nope. Great. All right. I want to talk about, this is the end of what we've been doing the past couple times. Has just been many, many examples over and over again of DFAs. I think we've had enough examples for now. So that can be sort of the end of our introduction to DFAs. I want to talk about what our book calls the formal description of a DFA. I don't know if you noticed, but all this time we have been discussing what our book would call the informal description of a DFA. And what's informal about it is I just sort of said a DFA is this thing with these circles and the arrows. This is a bit informal just because the circles and the arrows or whatever are not really traditional mathematical things, right? Mathematical things that we like to study are like numbers, sets, maybe geometric shapes, but we're drawing the DFAs as if they were like circles and arrows, but we're not really considering them to be geometric shapes. They're just helping us to indicate things on the diagram. There is, though, a real definition of a DFA in terms of set theory, and that's what I want to talk about. Now you may wonder what's the point of that if, like, I already told you what a DFA is and everybody more or less understood me. What's the big deal if I didn't say it in terms of set theory? I'd said it in terms of like arrows and circles. The big deal is that if you recall from my brilliant introduction on day one, which never made it onto YouTube, I'm still a little upset about that because I thought I did such an awesome job. If you recall, one of the major accomplishments of Turing and other people who created this whole body of work is that they were able to take an idea about what an algorithm is and translate it into very specific mathematical terminology. In particular, they were able to write down definitions using set theory. And this is what caused their idea to really go viral among mathematicians. Like it would, an idea in any kind of informal terms would not have been acceptable to the community, and that's why Turing had to do this work in the first place, because all they had was informalities and they needed something that was actually formal. So there is an important task of trying to express these ideas in unambiguous mathematical terminology, and these days we use set theory for everything in mathematics. So you know, you have a diagram, something like this, right? I will just, here's one as a very simple example. This is a DFA which accepts any string which has an even number of A's and some number of B's. It doesn't matter. As I have an even number of A's. Anyway, I would like to discuss, so we're going to sort of translate this into specific ingredients, which we will encode in a description using set theory. So we must, our formal description of the DFA must describe. Can anybody say what are the important ingredients here? I will get us started here on the list. The states are important. We have to say what are the states, like how many states are there? What else needs to be described to encapsulate, like you basically want to think about all the information that you see on this diagram. What is it? I mean, one thing is what are the states. What else?
The actual alphabet we use.
The alphabet that's used. I think I heard two people said something. Yeah, another is the alphabet. Somebody else said something else?
No, I just said the variables.
The variables, okay, yeah, that's the alphabet. Great. What else?
The accepting state.
Okay, which is the accepting states? Remember, it is allowed to have more than one accepting state. Most of our examples only have one, but there could be more than one. Okay, what else? I think there's...
The starting state?
Yes, the starting state. And I think there's one more important ingredient.
Is it every state needs an outgoing one?
Yeah, the arrows. Where do the arrows go, and what are the labels on the arrows? So these, I've always been referring to them as the arrows, but the sort of more technical word we use to describe them is the transitions. That is the arrows, but we're going to call them transitions more technically. All right, so there are 5 things here, and when we write the DFA in terms of set theory, we write it in 5 parts. So I'm going to tell you, so this, what I'm about to write here is a real definition of what a DFA is. We would say from a like sophisticated mathematical point of view, this diagram is a description of the DFA, or it's a visual representation of the DFA, but it's not what the DFA truly is. Its true nature is as an abstract mathematical concept. This is a picture of it, but what it truly is just a thing in set theory, and that's what this definition is. So the true nature of a DFA, let's call it M. You know, things in math generally you give a name to them. So let's call it M, is a 5 tuple. You know, tuple like a pair, triple, 5 things. It's called a 5 tuple, which has these 5 things written in order, and the 5 things are the same 5 things I have in that list, although they come in a specific order. I'm going to write it like this. M equals Q sigma delta Q0 and F. And then I'm going to tell you what each of those things represent. They are the same 5 things in that list up there, although they're not, the order in which I wrote the list is not the same as the order in which they appear down here. Actually, it almost is, but that's coincidental. Where? Okay, I have to tell you what each of these 5 ingredients is. Q is a finite set. This is the states. All right, so you write the set of states. Sigma is also a finite set. This is the alphabet. All right, delta. Now, delta is the most complicated part of this definition, but it is a representation of the arrows. And how are we going to represent those arrows in set theory is we are going to represent them as a function, because a function is a natural way which sort of, it takes one state and sends it into another state. So it's natural to try to represent those arrows as a function. And check this out. This is going to look a little crazy. This is called the transition function. And what you see here, that thing with the... let me just say the rest of this, and then I'll go back and try to explain this. This notation here is a little fancy. But let me just finish. The rest of this is simple. Q0 is an element of Q, and this is the starting state. Remember, every DFA has one unique starting state. And Q is the set of states, and so this thing here is an element of Q. It's one of the states, all right? And then F is the set of accepting states. This is a subset of Q. It is the set of accepting states. All right? These are the 5 ingredients that make up the official definition of a DFA. It has a set of states, a set which represents the alphabet, the transition function, one chosen specific state, which is the starting state, and then a subset of states, which is the set of accepting states. All right? Any questions about that other than the thing which I circled in blue, which I'm about to explain in more detail? The thing which I circled in blue is a description of the domain and the codomain of a function. This, I hope you remember from your discrete math days. You talked about the domain and the codomain. So the transition function is the most complicated part of this. The transition function looks like delta Q cross sigma to Q. All right, and what this means is, so this part here means the domain is pairs. That's what the cross there means. Remember the cross in set theory? This is the Cartesian product of 2 sets. It means the set of all pairs where the first thing comes from Q and the second thing comes from sigma. So the domain is pairs that look like Q, comma, A or something, where this is a state and this is a letter. And then the answer here, the codomain, this is the set which describes where the answer comes from. The codomain is, you know, just the set of states. So what it says is this is a function whose input is a pair, a state, comma, a letter, and the answer, the output, is another state. And this is exactly how those arrows are supposed to function, because the arrows have an origin state, they also have a letter on them, and then they point to some destination or some result state. All right? And so as a function, we express this as a state together with a letter, and the answer is another state where the arrow goes to. All right? So let's see if we can write down, this is the general definition of what a DFA is. Anyone having trouble reading this? I see some people doing this. Can I explain what? Is there something hard to read? No. All right. You can squint if you want to, but I'm happy to help. Okay. Let's try a specific example. So this is this is a little complicated, but once you know how to do it, it's not very hard to do this. How about that DFA that I just wrote before? It looks like this. This was an accepting state. Right? This was the DFA that I wrote before. Let's write the formal description of this DFA. All right. One thing that you need in order to write the formal description in detail is the states have to have names, and I'm going to give them very sort of boring names. Our book generally calls them S1, S2, S3, that kind of thing. So each state, I just give a random name. You know, sometimes you label the states in a way which makes it easy for you to understand what they kind of mean. That's not what I'm just trying to give them names so that we can write down all the abstract definition in specific terms. Okay, anyway, this DFA is M equals, okay, I'm gonna write the 5 tuple, and you have to write the things in the proper order. But the first thing is the set of states, and in this example, the set of states is S1, comma S2. Right? So that's the first part of the tuple. It begins with the set of states. Next is the set, which is the alphabet. What's that going to be?
Is it just A and V?
Yeah, it is the set A, comma B. Right? Make sure you put your little squiggly lines in there. If you leave them out, then you can't tell what's what. Okay. Next is the function delta. Now, it's not very convenient or even possible to write a function inside here, so I'm just going to say, I'll just put delta there, where I'm not going to be done. My next thing, what I'm going to say below is delta is, and then I'm going to describe what the function is separately, because you can't fit the description inside the tuple. Anyway, can we just finish off here? What comes next in the 5 tuple? The next thing is what I called Q0, the starting state. Which one should I put there?
S1.
It is S1, yep. And then, finally, the set of accepting states. What do you say?
Also S1.
Also S1, yeah, although I'm not going to write exactly the same thing here. Any extreme pedantic folks out there, what should I write here?
Do you want to use brackets again? 'Cause
Yeah,
it's a set.
you put the curlies around it because that is a set. Excellent. All right. So this is the description of the different parts of the DFA. The only thing which I haven't specified is exactly what is this function. Now, delta is a function, but it's not like a function that you would use in calculus where you can write like the equation, 3x plus 2 or something. It's not like that. It's just a function which takes one of these states and a letter and turns it into another state. So the only way to indicate this function is to actually write down every value of the function. And this is sometimes kind of tedious. It's not so hard in this example. So I'm going to just write down what is this function. I have to just say what are all the possible values of the function. Remember the inputs to this function, the domain of the function should be pairs, where the first thing in the pair is a state and the second thing in the pair is a letter. So you have to write down just every possible pair. In this example, there's only 4 of them, so it's not so onerous. And then for each of those, you say what the answer is according to the arrows. So when I see delta of S1 comma A, that means if I'm in state 1 and I do A, it goes to state 2. And so right here, I say this equals S2, right? And so on. You just have to, basically every arrow on the diagram translates into one of these answers, and you just have to look them all up. So delta of S2A, I look at S2, and the arrow with the A on it goes to S1. So the answer here is S1. And so on. I hope you agree with what I said. This is not hard to do. You just have to know how to do it and don't mess it up. Delta of S1 and B means from here, when I do B, it goes back to S1. So this is a S1. And then delta of S2 and B means from here, you do a B, you go back to S2. So this is S2. All right? And this is the complete description of that DFA right there. So according to folks like Turing or whatever, this is the true DFA. This diagram here is a helpful way to draw a picture of the DFA, but that's not really what the DFA is. What it is this right here. All right. And again, why wouldn't you be satisfied? Why don't you just say this is what the DFA is? Well, because that's just a picture of something. And of course, there are many ways you could draw the DFA diagram, and it would always be equivalent. You don't want your concept should not be like wedded to the diagram. The diagram is just a picture of what the DFA is. This is the DFA. All right. Any thoughts about that? We've only got a couple minutes. Would you believe me if I told you you can go the other way around? If I give you the formal description, it's not hard to draw a picture of the DFA, right? Like, let's just imagine. I don't think we have enough time to just invent another example, but could you look at this formal description and generate the picture just from that? I think you could. You know that there are 2 states, for instance. So I could just start, if I wanted to reconstruct the picture, I could just start with 2 states, right? We also know from here the alphabet is A's and B's. Now that doesn't make me draw anything particular yet, but and the delta also. Okay, I know S1 is the starting state from here, so I can stick the arrow like that. And from the last part there, I know that S1 is an accepting state, so I can say that's the accepting state. And then each of these transitions here translates into an arrow, right? And you can just fill in the arrows in the way you would like. So delta of S1A is S2, so that means when I from S1 and I do A, I go over to S2. Delta S2A means is S1, means when I'm in S2 and I do A, I go back to S1. And similarly, these give you these arrows. So you can go back and forth easily from the picture to this formal description, and then from a formal description to a picture if you want to. All right. This is the formal description of a DFA. And I think that's about all the time we got today. So we're going to talk a little bit more about the formality next time, and then move on to something else. All right. Do that homework. I'll see you.
Professor.
Yeah, I'll see you all on Friday.
Thank you.
Thank you.
Thank you.
Thank you.